Now we will discuss the motion of charged particle in non-homogeneous magnetic field. The result of non-homogeneous magnetic field is the variation of radius of curvature. This also induces a particle's drift. The gyrating charged particle gives rise to a magnetic moment, and we can define this magnetic moment here. Mu is equal to Ia, where I is the current due to particle gyration into area enclosed by the current. And since we know the magnitude of current, that is QB V perpendicular upon 2 pi r. Here V perpendicular is the component of velocity of charged particle perpendicular to the magnetic field direction. Pi r square is the area included by the current. We get the equation number 1, and by equating the Lorentz force with the centripetal acceleration, centripetal force, we will have the expression of magnetic field as mb perpendicular upon qr. From here we can have b perpendicular as q rb upon m. Now substituting the value of b perpendicular into equation 1, we will get the equation that we will get the expression of mu, that is the magnetic moment, as q square upon 2 pi m pi r square b, that is q square upon 2 pi m into phi. Here phi, that is pi r square b, this represents the magnetic flux associated with the loop. This can be shown that the magnetic moment remains constant if the variation of B is slow, either in space or time. Whenever there is a variation in B, an induced EMF will be generated due to the change in magnetic flux. So this induced EMF will be given by Faraday's law of electromagnetic induction as equal to minus d phi upon dt, which represents the rate of change of magnetic flux with respect to time. Numerically, this can be this will equal to pi r square dB upon dt, and we are concerned with the magnitude only, so we can write the EMF as pi r square dB upon dt. Now we can calculate the work done upon a charged particle in one orbit, and that will be equal to the product of charge and the induced EMF. We will have the equation second, that is work done is equal to q pi r square dB upon dt. We can also have the expression of work done using the expression of power. So work done will equal to, that is dw upon dt, that is power into time for one orbit, and we can have the expression, the equation 3, and Using the both equation, that is equation 2 and 3, we will have the two expression of work done, and by equating the both expression here, dw dt has been written as dw upon dv into dv upon dt. In this way, using the both equation, we will get that the equation 4, that will represent the rate of change of work with magnetic field, that is equal to QRV upon 2. And this expression, that is QRV upon 2, this expression has already been derived in the equation first, and this represents the magnetic moment mu. We can also have the expression of work done using the concept of magnetic potential energy and kinetic energy. Work done will be equal to half mv square or equal to magnetic potential energy. We can equate this as magnetic potential energy because magnetic moment mu has been placed in magnetic field B. From here we will have dw upon dB, that is b d mu upon dB plus mu. Comparing equation 4 and 5, we will have mu is equal to b d mu upon dB plus mu, and finally we will have d mu upon dB is equal to 0. That is, we finally got the result that the magnetic moment is independent of the magnetic field. For this magnetic moment mu to be constant, the magnetic flux phi must remain constant, because we have already shown in the equation 1a the mu is directly proportional to phi. Therefore, particle orbit is compressed as the magnetic field increases in such a way to maintain the magnetic flux phi constant. This means that if the particles enters in a filled region, from higher magnetic field to lower magnetic field, in order to keep the magnetic flux constant, the particles drift, a particle orbit will be compressed, because we are moving from lower to higher magnetic field region. And in the opposite case, when the particle is entering in a magnetic field where the magnetic field is, there is variation in magnetic field in such a way that particle moves from higher to lower magnetic field region. In that case, in order to keep the phi constant, the particle's orbit will expand with decreasing magnetic field. This property of charge particle in magnetic field, in variable magnetic field, is used to confine plasma.